Measure Integration and Analysis class. My name is Sunday Oluwafemi Odogbe, a PhD student in the Department of Mathematical Sciences. So today we'll be checking some exercises under section 2A, which theorems and basic definitions we have covered in our previous video. Alright, so let's see how many questions we can solve in this session. If we're unable to finish all the exercises, then we'll continue in the next video. So the first question, and this is related to the outer measure we have covered. So here's the first question. Prove that if A and B are subsets of R and the outer measure of B is 0, then the outer measure of A union B equals to outer measure of A. So as we know that we are going to prove two directions. So first we are going to prove that A union B is less than the outer measure, and then we are going to prove the other direction. Then we can now conclude, and this will now imply that A union B is equals to A. So let's start with the first one. Proof for the first case. So A note that since A and B are subsets of R, note by our set theory, you know that A is a subset of A union B. Okay, and that implies that the outer measure of A will be less than the outer measure of A union B. This is by outer measure preserve order. And then we are done with this part. So for the second part, we know that if we have B is a subset of, okay, so we can see that B is a subset of A union B union B, and then A union B take away A. Okay, does that make sense? Okay, we can just use countable subadditivity, that is A union B is less than A plus B. This countable subadditivity of outer measure. So since B is 0, then A union B less than A. So if we combine these two together, we combine this and this together, then that implies by star and star star A union being the outer measure is equals to the outer measure of A. Then we are done. So that is quite easy. So let's check the next question. Question 2. So question 2, suppose a subset of R and T belongs to R. Let T A be defined as T A such that A belongs to A. So we have to prove that the outer measure of TA is equal to the outer measure of mod T and outer measure of A. So note that proof if T is equal to 0, then trivially the outer measure of A will be equal to outer measure of 0 and A, and that will be equal to outer measure of 0, which is to be equal to 0, and then mod T of A is equal to the outer measure of 0 mod A, and this also will be equal to 0. So this equals to 0. So trivially, if T equals to 0, that actually holds. So let's assume T is greater than 0. Okay, so if T is greater than 0, let's define a sequence of open intervals that contain A. So let IK, then define, again let IK for K be a positive integer, be a sequence of open interval whose union contains A, that is A is a subset of union IKK equals to 1 to infinity. So if that be the case, then another sequence of interval TIK is a sequence of open intervals whose union contains TA. So that means that is TA is a subset of union K equals to 1 to infinity, and then TIK. So by the definition of outer measure, TA is less than or equals to the summation of the length of TIK, K equals to 1 to infinity, and this is equals to mod T summation K equals to 1 to infinity length IK, and taking the infimum and the infimum over all open sets whose union contains A, we have outer measure of TA will be equals to mod T will be less than or equals to mod T, and then outer measure of A. So that is one direction. So let's prove the second direction. Let's divide another sequence of open interval. Let's JK for k positive integer. Let jk be a sequence of open intervals whose union contains TA. So we cannot have that. So that is what we mean is that TA is a subset of union jk, k equals to 1 to infinity. So then jk times 1 over t is a sequence of open interval whose union contains 1 over t into bracket t a. Okay, that is 1 over t a, they are subset of union 1t jk, k equals to 1 to infinity. So if we take the outer measure, by the definition, outer measure of 1 over t times ta will be less than summation k equals to 1 to infinity, the length of 1 over t jk. Okay, and this is equals to 1 over t summation k equals to 1 to infinity length of jk. Okay, don't forget that the length of jk is our jk's is a sequence of open intervals that actually covers ta. So that means that this is equals to 1 over ta and the outer measure of ta. So let's write what you have to have there. So we have 1 over t times ta less than mod 1 over t, and that is mod 1 will be 1 over mod ta times outer measure of ta. So this t cancel this t, so we have mod a is less than 1 over mod t outer measure of ta. So if we can cross multiply this, then we have outer measure of mod t that's outer measure of a is less than outer measure of ta. And that is the second direction. This is the first direction. So then we have the second direction. So if you combine this together, so this implies that mod outer measure of ta is equals to mod t times outer measure of a, and that conclude that question. So that is next one. So let's go to problem 3. Problem 3. We have proved that if a, b are subset of R, and then outer measure of A is finite, then we have to prove that the outer measure of B take away A is greater than or equals to outer measure of B minus outer measure of A. Okay, so we want to prove that B take away A is greater than outer measure of b minus a. So since a is finite, we can rewrite this as b take away a plus a, which is greater than or equals to b. So let's prove now. Proof. So since a comma b are subset of R, so note that b is subset of b a union b, sorry, a union b take away a. So you can carefully check that not set notation. A union b take away a. Okay. So with that, then we are almost done with our proof. So you can verify that if that actually holds. So then the outer measure of b is less than outer measure of a plus outer measure of b take away a. So this is outer measure preserve orders, preserve order, and countable subadditivity, countable subadditivity. So then we can rearrange. Since a is finite, then we have mod b minus a less than b take away a, and then that gives us the proof. So that is also a nice question. So let's go to question number 4. So we have, suppose F is a subset of R with property that every open cover of F has a finite subcover. So we have to prove that F is closed and bounded. So the first thing is proof 1. F is closed. So that's the first thing we want to prove. So we're going to prove this by contradiction. Prove by contradiction. So assume F is not closed. So what does that mean? So this means there exists a limit point x of F, but does not belong to, but x does not belong to F, but F belongs to the closure. Okay, so let's construct an open cover of F. Construct an open cover of F. So for each n positive integer, so let un equals to F intersection the open ball Okay, or you can also write it in this form: x minus 1 over n common x plus 1 over n. So this interval cover all points in f close to x. Okay, so that means that we need to add one more open set. So add another open set G, which is equal to R take away x. Because this un already cover x, then we just need to include the point which this does not cover, which is R take away x. So you see that then. So this covers f far from x. So that means that we have a nice open cover now. So the next thing we need to verify is that can we actually find a finite cover from this open cover we have defined, which will actually cover the whole of f. So suppose we choose a finite cover, if that is possible. Suppose we choose a finite subcover, but since x is a limit point, of f, so no finite number of UNs can fully cover. So you can check our video in order to understand what a cover and open covers finite subcover means. Can fully cover all the points in f near x. So that is not actually possible, and hence the finite subcover would miss some points of f near x, and this contradicting the assumption from the hypothesis that our open cover has a finite subcover. So, and that shows that so f must contain or its limit point. So if it contain all its limit points, so meaning f is closed. Alright, so the next one is 2 f is bounded. So prove by contradiction also. So assume f is not bounded. So this means that for every m greater than 0, there is always some point x that belongs to f such that mod x is greater than m. That is, f has points going off to infinity. So let's construct an open interval for this, an open cover, and see if we can find a finite cover that will actually cover that our f, including the point x. So defined our open cover to be equals to minus n comma n, such that n belongs to positive integer. So where each n, where each interval is an open interval. So each open interval cover all points of f, right, that lie within distance n of the origin. So, and actually each of these cover all points of R, and since f is subset of R, then minus n comma n also covers R, also cover f. So now the next question we want to ask ourselves is, can we find a finite subcover that will cover f? So a finite subcover would consist of finitely many intervals. Let's see, minus n1 comma n1 minus n2 comma n2 dot minus nk comma nk. Okay, where nk is the largest, right? Is the largest finite subcover. But the challenge now is that, however, since f is unbounded, there are points, there will be some point x that belong to f such that the mod x is greater than m, that will be greater than nk. So it will not be covered by this guy, which are not covered by this finite subcollection, and that contradicts our assumption, right? So this contradict shows f shows that f must be bounded, or else the hypothesis will not hold, and that completes that question number 4. So next we have question number 5. So question number 5, we have suppose fancy A is a set of closed subset of R such that the intersections of all those guys are empty. We have to prove that if fancy A contains at least one bounded set, then there exists n positive integer that is a finite, or we call it a finite set that belongs to fancy A such that their intersection is also empty. So this is a nice question. Let's check the proof. So the problem asks us to prove that if we have a collection of closed subset of R with empty intersection and at least one of these sets is bounded, then we can find a finite number of sets from this collection whose intersection is empty, and this is related to the finite intersection properties and compactness in topology also likewise. However, let's just stay between our ring analysis. So let's consider the bounded set. Let's consider the bounded set. So let B belong to our fancy A, be a bounded set in the collection. So since B is bounded, and by definition of a bounded set, there exists a M, even where M greater than 0, such that B is contained inside that interval. So let's consider the complement set now. So for each F that belongs to fancy A, let's define the complement of F to be R, take away F. This is for each F now. Then you realize that since F is closed, then the complement is open. Right? The complement of a closed set is open. So let's use the given condition. So given that the intersection of all F that belongs to A of F is empty, so this means that R can be covered, or R is just the entire of the complement union, the union of all the complement, which is an open set which actually contains the entire of R. So let's consider the bounded interval we have. Consider the interval. For the interval, we have minus m. So, and then we have this to be subset of F complement F belongs to E. So if this can be covered by R, then this also should be, then the complement, this open cover also should cover minus m, still m, no matter how large m could be. So we can now apply one of the theorem we proved in our previous video, which is Bohren theorem. So since this is a closed bounded set, so the Bohren theorem said that if this is closed and bounded in R, then we can find a finite collection. There exists a finite subcover for this our open cover. So apply Embury theorem, then instead of making use of the open interval, you can make use of finite subcover. That's one of the applications of Embury theorem. So taking the complement by De Morgan's law, so we have that this intersection F1C union F2C union Fn complement is actually equal to, because of space now, and we do this. So is equals to minus m common m intersect the complement of this guy. We just the complement of this complement, we change the unit to intersection. By De Morgan's law, we have F1 intersection F2 intersection intersection Fn, and this is equal to empty set. If this is equal to empty set, then F1 intersection F2 intersection Fn also equals to empty set. Right, because this is not empty, this is not empty, so if the intersection is empty, that means that this must be empty. And also this intersection, this is not empty, but if you take the complement, then it makes the both sets not to have anything in common, and then we have this, our proof being done. Okay, so let's see if we can still check. So let's check one more question here, and that's question 6. For the question 6, we have this. We have proved that if A, B belongs to R and A is less than B, then we have to prove that this condition holds. Alright, so note, before we start the proof, note that if A, B belongs to R and A is less than B, then the outer measure of a closed bounded interval is equal to B minus A. In other words, we can exchange these points to be this. That means that it suffices for us to show that this is equal to A, B is equal to A, B half closed here equals to A, B. So we can start picking one after there. We can use to prove this, to that this equals to this equals to this. First, proof, claim that A, B is equals to A, B. So let's first of all use the inclusion, or we call outer measure piece of orders. So since this is A, B, this does not include A, it does not include B, right? So that means that this should be a subset of A, B. Okay, and that implies by outer measure A, B is a subset of outer measure of A, B, and that holds. So that is the first direction. So the second direction, let's we can define some sequence of open interval that will cover this. So let external greater than 0. So there exists an open cover as a minus e comma b plus e that cover a comma b. Okay, so if that holds, then we have a comma b to be less than so so since this can be covered, this open interval can cover this, then for sufficient small external, this small external, then the outer measure of this open interval should be greater than a comma b minus 2 epsilon. Okay, and since epsilon is arbitrary, then the outer measure of a comma b is greater than the outer measure of a comma b. So if you combine these two together, and then we have shown plus that a comma b is equals to the outer measure of a comma b, which is equals to b minus a. So the second, we have half of ab to be equals to a comma b. Clearly we can also, so we can cover a comma b with a minus external b plus external for external greater than 0, and since a comma b is subset of that, so the outer measure f comma b has to be less than a comma b. Alright. If you go through this, you can just have b plus e minus a minus e, which is equals to b minus a, minus 2a, and since this should be plus, and since epsilon is arbitrary, this is equals to b minus a, which is actually equals to a comma b. So that is the breakdown of that. So in the other direction, since the half interval is subset of the closed interval, so we can cover a comma b with a minus external b plus external. So for sufficiently small external greater than 0, so we have the outer measure of the half interval will be greater than the outer measure of A, B plus minus 2 externum, and 6 externum is arbitrary, then 6 externum is arbitrary, then the outer measure of the half interval is greater than the measure of A, B. So if you combine these two together, then you are done. A, B is equals to A, B, that's equals to B minus A star and star. So then you can try this on your own. Third, you have to show that the half, third one, the half closed interval is equals to B minus A. So we stop here in this video. So in the next video we try to give the solution for the remaining question, and that will be question 7 down to question number 14. So hope to see you in the next video. Thank you.